In this video, we're going to work example problems where we find volumes of solids using integration. Specifically, we're going to use the method that was developed in the opening section on this topic of finding volumes using integration. And so this method was that, so the volume of a solid is equal to the integral from A to B of A, and let's say the independent variable is x, A of x, dx. And the idea is that, so this A of x is a formula for, if you can imagine you lay the solid along the independent variable axis, the way it's oriented doesn't matter, and then the back end of the solid is at x is equal to A, and the front end at x is equal to B, or whatever the independent variable is. And then anywhere between A and B, so if you're at some x value between A and B, what you can imagine is, you can imagine a plane that's perpendicular to the x-axis, and that's going through that point you're at, that x point you're at, and it cuts the solid. And that cut it makes a cross-sectional area. The area of that cross-sectional area, that's the value of this function at that x. So you can imagine each x between A and B is going to have a different cross-sectional area. Okay, now, so if you take that area and multiply it times dx, or a delta x, what you've got is a right cylinder. And so what you're doing is this method is that you're taking the volume and you're breaking it up into these small right cylinder pieces. And a right cylinder, so you might think right cylinder is like that, but this is a certain type of right cylinder. This is a right cylinder with circular bases. In general, a right cylinder is, so you've got these two areas they're planar. These areas are in a plane, and these two planes are parallel and just separated. But these areas can be any shape, but they're the same. These two areas are the same shape, and they're just separated from each other. And then you imagine you connect all points on these areas, on the edges and inside, by lines that are perpendicular to the planes, and that creates a right cylinder. And so that's the principle of this integration method. To solve for a volume, we break the volume up into pieces, these small pieces that are right cylinders, with the bases of each right cylinder being the cross-sectional area of a plane that cuts the solid at that x point. And so it's this method that we're going to use to find the volumes of each solid in this video. Now, in the previous video, we found what were called solids of revolution, and these solids had a symmetry about a center axis. And the idea was you have an area, and you imagine rotating that area about an axis to create a solid. But to get these volumes, we still used this formula. Solids of revolution were, the volumes of solids of revolution were determined using this formula. We still just found a formula for this A of x for the solid of revolution, and then applied the integration. But for the problems in this video, we're going to use this formula a little more generally, not for a special case of a solid of revolution. And so I wanted to mention all of these details before we started these problems, because it's important to note which technique you're using, because we're going to see in the next section that we're going to develop another integration technique for finding volumes. So it's important to note what integration technique you're using. Okay, so let's get started. So for each problem, we're going to be given a solid, and we want to find the volume of that solid. So here we want to find the volume of a frustum of a right circular cone with height h, lower base radius capital R, and top radius lowercase r. And so the main challenge is finding that cross-sectional area formula. And so you want to choose the independent variable axis, or you can think about how you're orienting the solid along the independent variable axis that's most helpful for finding that cross-sectional area formula. So if we, there's this axis of symmetry here going down the center, and so we can use this is we'll call it the y-axis. We'll use this as the independent variable axis. And, we could consider so we could look at this as a solid of revolution problem where you revolve this area here about this y-axis. But we just worked a bunch of solid of revolution problems in the previous video. This video is more about applying that volume integration formula more generally. And we're going to see for upcoming problems, we can't use solid of revolution even if we wanted to. So let's try and just get a cross-sectional area formula here more from scratch. And so the idea is, so we're going to say we're going from, this is 0, so we're going from 0 to h along the y-axis. And so what we need is a general formula for if we're at any position y, what is the radius of this cross-section? We'll call that r star. All right, so we're at this position y, then there's a plane that is perpendicular to this y-axis that goes through this point y, so it cuts the solid, and there's a cross-section, and we know that's going to be a circle. What's the radius of that circle? We'll call it r star. Okay, so we can see, though, that r star is going to vary from lowercase r to uppercase r, and r star is going to go from lowercase r to uppercase r, and it's going to do so linearly. We can see that here. So it's going to increase linearly from lowercase r to uppercase r. And so to get a formula for r star, let's get 2 points on that line. And so if we imagine the input's going to be y, and the output's going to be r star, and so we can see that when y is equal to 0, r star is going to be lowercase r, and when y is equal to h, r star is going to be uppercase r. And so with that, we have 2 points, we can get a slope. So let's say we've got, this is y, let's say this is the second point. So y2 minus y1 over x2 minus x1. So there's the slopes. Now we can use the point slope formula. So y minus y1, and let's use, this is a simpler point here, so we'll use that first point. So y is it's the dependent variable. Y minus y1 would be, so r is equal to m times x minus x1, so just times y. Okay, so r star as a function of y is equal to and there we go. So with this isn't the formula we're looking for, but we've got the radius of each of the circle at each cross section. So the a of y, which is what we're looking for, a of y, because what we're going to do is this volume is going to be from 0 to h, a of y dy. Okay, so we're trying to find the a of y. That's just pi r star squared. So pi, and then r star squared. Okay, so now let's simplify this. So if we expand this here, we get, so we've got this squared plus r times this plus r times this. So 2r and then plus this squared. So there you go. There's a of y. So now all we got to do is just integrate a of y with respect to y from 0 to h. All right, so we can bring the pi out front of the integral. So from 0 to h. And there we go. That's the volume of this solid here. So we've got, so capital R, lowercase r, and h are constant. I mean, they aren't functions of y. So this, this looks complicated, but we really just need to focus on the y terms, integrating the y terms. So we've got right. So if you take this derivative with respect to y, you get this term plus okay, so this evaluated from 0 to h. Okay. So when we plug in 0, this term goes completely away, so we just need to evaluate this at h. So we've got okay. So this cancels here, this cancels here. We've got okay. So let's factor out a 1/3 and an h. So we've got okay, so let's see if we can simplify this a little bit more. We've got, so, okay, capital R squared minus 2 plus R squared plus 3 okay, so these cancel and we're left with, so capital R squared plus lowercase r squared, and then these are the same terms, so this would be plus lowercase r capital R. And there you go. That is the volume. Pretty cool. So this is in general. So it's for any frustum. You could just did whatever for any dimension. This is the formula for the volume of that frustum. Okay. So here we want to get the volume of this cap. This is a portion of a sphere. And so, yeah, so here we can't use any, well, actually we could maybe use a solid of revolution. It would be a little more difficult, but yeah, we would do, but yeah, well, we're not going to use solid of revolution. We're just going to try and come up with a general formula for the cross-section as a function of an independent variable. So, and then just integrate along the length of the solid. So what we can do is, this is an axis of symmetry. We'll call that y again, just because it's straight up and down. And again, we just want to get a formula for the cross-sectional area as you walk along. So we're going to be walking along from y is equal to, so this will be the starting point, this will be the ending point. And so the a will be, so we're going to be integrating from a to b, and the independent variable is going to be y, so a of y dy. The a is going to be, you can see it'll be r minus h, and the b will be r, right? R is the radius of the sphere here, the whole sphere. So we're going to have to make a distinction between the radius of the cross section and the radius of the sphere. So you see the radius of the sphere minus h gets you there to A. Just the radius of the sphere gets you to B. Okay? And so how can we get a formula for, you know, a general formula for this? We'll call that R star again. R star is going to go from, it's going to start at this value and then end at 0. And so to do that, what we notice is this. We can notice that this here, this is R, right? And then for any, so here's just a general radius. We're trying to get, we want to get, this is R star. And so if we look at it that way, let's do this. So here's R star, right? And let me draw the circle so you could see it. There's R star, and then we can see that this is R. And so we can use the Pythagorean theorem with this being what? This is, we're going from, so we're starting at y is equal to r minus h. So this is y is equal to 0. And then and so that's why we're integrating from y is equal to r minus h to y is equal to r. And so for any general position here, that's going to be equal to, well, it's just going to be y. This is y. This distance here is y, right? Because we're integrating from y is equal to r minus h to r. And so this whole distance here is just y. And so r star squared plus y squared is equal to r squared. And so r star is equal to the square root of r squared minus y squared. For any position y, as you're along this, going from r minus h to r, for any position, if you want the radius of that cross section, then just take the radius of the sphere, square it, and subtract that from that y value. That's going to be somewhere between r minus h and r. Okay, so with that, a of y is equal to pi r star squared, which is pi r squared minus y squared. And so there we go. So the volume is, we're integrating from r minus h to r. We can bring the pi out front. R squared minus y squared dy. And that's it. So we've got, so pi, and then y r squared minus 1/3 y cubed from r minus h to r. Okay, so pi, now let's plug in r, so r cubed minus 1/3 r cubed. Okay, minus, then we've got r squared times r minus h minus 1/3 times r minus h cubed. Okay, now we just need to simplify this. So, okay, so we've got 1 r cubed minus 1/3 r cubed, 2/3 r cubed. And then here, we can, let's factor out an r minus h. And so what we've got is r squared minus 1/3 r minus h squared. And actually, to make this a little bit easier to work with, let's do this. Let's take out a 1/3. So that would, we'd have a 3 here and just nothing here. Just r minus h squared. Okay, so now we can factor out a 1/3 from the entire equation, and we've got 2r cubed minus r minus h like that. So now it will be easier to simplify. So we've got 2r cubed minus, and then 3r squared minus r squared minus 2rh plus h squared. And if we distribute this minus sign, we get plus minus. And so we've got two r squared plus 2rh minus h squared. Okay, and so this is 2r cubed minus, and then we've got 2r cubed plus 2r squared h minus rh squared minus 2r squared h minus 2rh squared plus h cubed. Okay, and so this is 2r cubed minus, and this is, so 2r squared h minus 2r squared h. So this goes away. Then you've got, so okay, so 2r cubed minus, oh wait, no, 2r squared h minus 2r squared h. Okay, so we're left with 2r cubed minus rh squared minus 2rh squared minus 3rh squared, and then plus h cubed. Okay, so this is 2r cubed minus 2r cubed plus 3rh squared minus h cubed. So these cancel, so we've got 3rh squared minus h cubed. And so we can factor out an h squared and there you go. That is the volume of this piece of the cap of the sphere. Okay, so now we've got a frustum of a pyramid with square base of side B, square top of side A, and height h. So this is a square pyramid. And so we can, we just need a formula for the cross-sectional area based on some variable. So if we just put an axis going through the center of this, I mean, we could put this axis anywhere, it doesn't matter, because all we're going to do is, so we want to get a function for this, a function that gives us the side of the square. That's what, because then once we have the side length, then we could just square that to get the area. And so we can see that it's going to, the side length is going to vary linearly from A to B, right? You can see this is linear variation here. And, you know, I guess this will be the 0 point, and we'll go from 0 to H, right? The height is H. This length of this line here is H. We know that because this line is perpendicular to the bases. And so, I mean, this could be 0 and this could be H. It wouldn't matter. I mean, you get the same result, but we'll say this is 0. And so we need a function. Let's call this X. We're going from X is equal to A to X is equal to 0 to X is equal to H. And then when X is equal to 0, so we have X, input X, output is the side length. We'll say S for side length. Okay, and so when X is equal to 0, the side length is equal to A. When X is equal to H, the side length is equal to B. And so now we want to make a formula, a linear formula that's based on these 2 points here. So the slope is going to be, we'll say this is point 2. So y2 minus y1 over x2 minus x1. Okay, so now we can use the point slope formula, and we'll get, so y, I'm saying y, that's the dependent variable, so y, we'll call it S for side length. Y minus y1a is equal to m times x minus x1, so just times, this would be x. So S as a function of S, the side length as a function of x is b minus a over hx plus a. Okay, so now for any point x, the area, so the area, the cross-sectional area is just S squared. Right? And so all we need to do is integrate from 0 to h this a of x dx. That's the volume. So, okay, let's expand this so we can integrate it. We've got this squared, so it'll be b minus a squared over h squared x squared plus, then it would be 2a b minus a over hx, right? So it's this times this plus this times this, plus a squared. Okay, so we're integrating this from 0 to h. So we've got, you know, b, a, and h aren't functions of of x. So what we've got is 3h, so okay, and then all right, so we're integrating this from 0 to h. And so when x is equal to 0, this just is nothing. So we just need to evaluate this at h. Okay, so we've got, when this is h cubed, this cancels and we're just left with h. So we've got h over 3. Okay, now here, when we plug in h, we get h squared, so we're just left with ah b minus a, and then we've got ha squared. All right, so let's simplify this a bit more. So we've got h over 3b squared minus 2ab plus a squared plus hab minus a squared h plus a squared h. So these cancel. We've got, so 1/3 hb squared minus 2/3 hab plus 1/3 ha squared plus hab. Okay, so minus 2/3 hab plus 1 hab is 1/3 hab. So 1/3 hb squared plus 1/3 ha squared plus 1/3 hab. All right, so the volume is, we can factor out a 1/3 and an h, and we're left with b squared plus a squared plus ab. Okay, that is the volume. Now, what happens if a is equal to b? If a is equal to b, then the volume, if a is equal to b, we've got 1/3 h, b squared plus b squared plus b squared. So this is 3b squared times 1/3 h, hb squared, which, yeah, it makes sense because it's just the two bases are the same. It's either hb squared or ha squared, same thing. That makes perfect sense, right? This is just, you have a rectangular prism. Okay, if a is equal to 0, what do we expect? Okay, well, it's going to be like, it's going to come up to a point. So I mean, I don't know what that would be, but if a is equal to 0, then, so this is v when a is equal to b. Okay, with v when a is equal to 0 is 1/3 h b squared. Huh. So it's not hb squared, it's 1/3 hb squared. Okay, let's find the volume of a pyramid with height h and base an equilateral triangle with side A. All right, so the idea here would be that, so okay, we're trying to find a cross-sectional area formula, and so we'll put the independent variable axis going down the center here, and we're going to go from, I guess we'll go from the top, will be like the origin. So we're going to go from 0 to h, right? So like right here. That's the height. So this axis is perpendicular to the base. So we're going to go from 0 to h. And this will be like, we'll call this the x. So from 0, x is equal to 0 to x is equal to h, we want to get for any point x within that interval a formula for the cross-sectional area. That's, you know, we take a plane that's perpendicular to this axis. So it cuts through the solid, and there's going to be some cross-section. What's the area of that cross-section? Well, okay, we can imagine that each cross-section is going to be an equilateral triangle, right? It's equilateral triangle all the way to the point. Okay, so we just need a formula for the side length of the equilateral triangle at some position. Well, it's okay, that side length is going to vary from a to 0 linearly. We can see it's linear, right? We can see it just goes from a and then linearly goes down to 0. So what we need is, so we have 2 points. So we in general, it's x and then side length. We input an x, we get a side length. Okay, so what points do we know? When x is equal to 0, the side length is equal to 0, right? When x is equal to h, the side length is equal to a. So m is, well, this is 0.2, this is 0.1, so y2 minus y1 over x2 minus x1. M is a over h. All right? So now we can do the point slope form. So y, let's use this point, it's the simplest. Y minus y1. So what is y? Y is s. S minus y1 is 0, is equal to m times x minus x1. There you go. There's the side length as a function of x. When x is equal to h, s is equal to a. When x is equal to 0, s is equal to 0. So now the formula for the area of an equilateral triangle, if you Google that, the area of an equilateral triangle is root 3 over 4 times the side length squared. So the area formula as a function of x is root 3 over 4 times this s squared. So root 3 over 4 a squared over h squared x squared. And there we go. So now we just, the volume, we're going to be integrating from 0 to h, root 3 over 4 a squared over h squared x squared dx. Just like that. That's simple. So, you know, these are all constants here. A is not a function of x. H is not a function of x. Root 3 over 4, obviously, it's just a constant. So we can take out all the constants from the integral. You might say, well, what about h? H is a variable. No, remember this, the limits of integration have nothing to do with the actual integral until the end, until the end. So when it comes to like finding the antiderivative, these are all constants. You can take them out. So, all right, so we've got, we're evaluating this from 0 to h. This is x squared. Okay, so we've got 1/3 x cubed evaluated from 0 to h. Okay, so we take out that 1/3. And then this is just h cubed. So these cancel, and we've got root 3 over 12 a squared h. And that's the volume.